Okay. I would like to share with you our recent research in a very curious field. I want to tell you about, this work was accomplished together with my collaborator, Yuri Yerin, who was graduated in Kharkov. Then he worked in the Institute of Low Temperature Physics in Kharkov, and now he already 4th year works with me in Italy. And our co-author is Caterina Petrilla, professor of Perugia University. So the title is Topological Phase Transitions Between the Gap and the Gapless Superconducting States. Sorry, why? Okay. So outline of my talk will be, first, I want to remind what is a gapless superconductivity. The second reminder will be the transitions of the 2.5 order. Then I will ask myself, what is the order of the gapless transition in superconducting state? Then I will propose you some topological interpretation of gapless transition in superconductors, and I will discuss the stability of Abrikosov-Garkov mean field description with respect to special fluctuations of the magnetic impurities concentration. Experimental manifestation will be proposed to study by means of thermoelectric effect. Okay, let's return in the year 1960, which is crucial for my discussion. In this year, in JET appeared almost simultaneously 2 articles. First one was the article of Abrikosov and Garkov. I want to recall you that the microscopic theory of superconductivity was created by Bardeen, Cooper, and Schrieffer in 1957. And they established the rigid correspondence between the superconductivity and the gap in the spectrum of quasiparticles. So this was the fundamental point of the microscopic theory of superconductivity. In 1959, Abrikosov and Garkov proposed the so-called cross technique, which allows to take into account the effect of impurities on properties of superconductors. And they found what today we call Anderson theorem, that normal impurities in the first approximation does not affect on thermodynamics of superconductors. Nevertheless, in 1960, they extended their approach to paramagnetic impurities. So impurities with the spin, with magnetic moment. And as a result, they found some, you can see here, some, okay, just as images, the elements of their theory. But what was important that they demonstrated that naturally, because ferromagnetism and superconductivity are antagonistic phenomena, so adding of paramagnetic impurities kills you superconductivity, gradually kills. But then exists naturally some concentration which kills completely. But at 91% of this concentration happens something strange. You have superconductivity and you do not have gap in the spectrum of quasiparticles. So what happens, you see that at the left figure, you see the normal gap structure for density of quasiparticle states. Then at some concentration, which is 91%, the gap is closed, and then you have some gapless state. They calculated the density of electron states as a function of energy and found some transcendental equations which describe all this. Very nice. Now I will return to Kharkov in the same 1960. Ilya Mikhailovich Lifshitz. He studies the effect of topological changes. These years, he was his group with Moisei Kaganov and other people, they they were creating the fermiology. And among other studies, he studied how the change of the number of the components of connectivity of Fermi surface affects on its thermodynamic properties. And he found that when you have the break of the void, of the neck, or formation of the new void of Fermi surface, in thermodynamic potential appears some non-trivial contribution proportional to the closeness to this transition, to the critical point. This correction to the thermodynamic potential is proportional to the power 5/2. And correspondingly, in the density of states, which is the second derivative, you will find the square root of the closeness to the critical point where these topological changes happens. Very good. Now, why it does not move? Sorry, something with my, yes. I want to recall you that in 1933, Paul Ehrenfest classified phase transitions based on the behavior of the thermodynamic free energy as a function of it. So he identified the order of phase transition with a number of derivatives of thermodynamical potential, which breaks. It is why we call the superconducting transition as a second order phase transition, ice-water first order transition, and Lifshitz in this spirit called his transition 2.5 order phase transition, because it is a third derivative which breaks, but it breaks as a 1 over square root. So this was called 2.5 order phase transition. Very good. So now I don't understand. Yes. So what was discovered? A lot of people were involved in Ukraine in these studies. Baryakhtar, for instance, with Makarov, studied the effect of 2.5 order transition on superconductivity. Mikhail Alexandrovich Krivoglas studied such transition in alloys. So nevertheless, all this early period of studies of Lifshitz transitions were restricted by the smallness of the effects. In 1981, Valery Yegorov studied what happens in the lithium-magnesium alloy when we change concentration of lithium. And he found that if thermoelectric power is the monotonic function at room temperature, some bump grows at nitrogen temperatures, and then increase it maybe 5 times happens at the helium temperatures. The same kind of experiments were done on molybdenum rhenium alloys, bismuth stibium, etc. So how to understand what happens with thermoelectric power close to Lifshitz transition? And I want to recall you some trivial formulas. This is a Drude formula. And you see that I can get it very easily from Boltzmann equation, from kinetic equation. And here I have the cosine square in denominator, and here the constant. And this integral is easily carried out, and you have Drude formula. If I calculate the thermoelectric coefficient here, instead of one of the electron charges will appear electron energy. And in the result, this integral will be 0. So there is no thermoelectric effect. Indeed, if you do not take into account electron-hole asymmetry, you will not have thermoelectricity. So to get non-zero result, it is necessary to derive this, to find the next orders of next terms in expansion of the density of states, V Fermi squared tau relaxation time as a function of energy. In result, you will get some Seebeck formula, very small. The Seebeck coefficient is normal metal, is T over mu, T over epsilon Fermi. This is very, so this is typically 10 microvolts per Kelvin. Okay, let's go ahead. No, sorry, okay, yes. So in 1985, I proposed the microscopic theory of this phenomena. So we formulated in green function technique and we found indeed the behavior of relaxation time close to transition. What was the reason of this anomaly? What is the physical reason of this anomaly? Physical reason is that you have peripheric large piece of Fermi surface and small one. And you have different types of scatterings. Electrons can scatter from periphery to periphery, and it will give you normal small thermal electrons. But you can imagine the processes when the electron being scattered on impurities finish in the small void. And this is a trap. In the result, the electron here has a zero velocity, and it is necessary to wait a long time to return. Such contribution, sorry? Yeah, such processes give you non-trivial contribution, energy-dependent contribution in tau, and in result, this produces you this peak. These curves are theoretical, and they very good reflects what happens in experiment. Very good. So now, so the topological treatment of transition, of Lifshitz transition is evident. Changing the, creating new void of Fermi surface, you change the number of the components of connectivity. And you have some special part of Fermi surface which is separated from the main Fermi surface, and you have special contribution in tau. This produces you giant thermoelectric effect. Okay, but what is the order of the gap? So this was introduction. Now I will speak about the paper. So what is the order of the gapless transition in superconductor? This question no one asked before us. 60 years passed. These two papers, Abrikosov, Garkov, and Lifshitz, existed, and they generated huge number of thousands of following papers, but these two flows did not intersect. Now we asked ourselves, what is the order of gapless transition? The answer is very simple. Actually, it was enough to open the paper of Ambigyakar and Griffin of 1965 and take free energy, which they calculated at zero temperature. Then you calculate third derivative and you find exactly Lifshitz situation. So you find that by some reasons, the transition, when you add paramagnetic impurities at zero temperature to superconductor, so in it happens in terms of Ehrenfest 2.5 order phase transition. But if Lifshitz treatment was very simple, it is a change of the numbers of the components of connectivity. Here, Fermi surface does not mean too much for superconductivity. Absolutely other situation. How to understand it? So we calculated the density of states, which was actually well known. And then what was our contribution? Because this two-dimensional picture did not give me any possibility to understand what happens from the point of view of topology. Must be some equivalence between Lifshitz and between this transition, both of them of the 2.5 order. So what we did, we proposed to treat this transition in the some specific space. Namely, we proposed to present the surfaces of the density of electron states close to the gapless transition as a function of energy, naturally, omega. And then I study here, the third variable is the order parameter of superconductor in the absence of paramagnetic impurities. So at the very beginning. So I study the series, the set of superconductors with different delta, and I get this figure. I want to recall you that in some sense, I repeat the way of Lifshitz, because the Lifshitz transition in different systems can be realized in different ways. For instance, the cited by me lithium magnesium alloy, actually you study it as a function of concentration of lithium. So you have the series of alloys. So I do more or less the same. So how to characterize these surfaces? And I want to say that I see the analogy. Please look, this is a representation of density of states function as a function of omega and parameter which drives transition, zeta, 1 over tau s delta. And here you see the break of the neck in Lifshitz transition. You see the topological evolution of the density of states in the omega zeta space from the gap state to the gapless state, combined with a similar topological behavior of the Fermi surface, demonstrates me the equivalence. So then I want to do the third excurse and to record you what is the Euler characteristics. All of us remember the Platonic solids, regular convex polyhedrons. You remember that Kepler put them in the basis of his vision of the universe. For Platonic solids, the Euler characteristic is the sum of number of vertices plus facets minus number of the edges. So for Platonic solids, it is 2. If I will now calculate the Euler characteristics for, it is possible to do formally through the Euler-Poincare integral. So if I will calculate Euler characteristics for surface of density of states in different states, so this is a gap state, so this is a critical point, and this is gapless state. So I will see that here narrow and hollow between two glued sheets of the DOS surface. Okay, so here appears so-called cuspidal edge. We did not know all this, we studied. So what happens here is a catastrophe phenomenon in omega delta space. And so we see that actually what happens here from topological point of view, there is a change in the Euler characteristic. One can, it is possible to see what I say in two ways. Or one can perform the polygonization of those surfaces and evaluate the Euler characteristics in a similar manner as with Platonic solids, or to calculate the Euler-Poincare integral, which we did. Very good. Now I want again compare the Lifshitz transition in metal and in superconductor. Please look at this picture. You see our results in the space omega delta n. And here I present the two types of Lifshitz transition. Here you see the break of the neck, or the transformation from two-sheet ellipsoid hyperboloid through conic point to one sheet. Here you see the analogous, always higher number of components of connectivity, the Fermi sphere with some small void disappears, and the only Fermi sphere. And in this topological evolution, you see that here, as I told, the so figure here I told you was Euler characteristic 0, 1, 1. Here in figure D, the two-sheet hyperboloid, where each sheet is topologically equivalent to the disk with He equal 1. The Euler characteristic of the disjoint union of two disks is the sum of their Euler characteristics, so He equal 2. In figure E, the cone could be simplexized into 6 singular two simplexed given. Okay, I will not go in details, but there is the message of this slide is the following. Lifshitz proposed the simple treatment of his transition in terms of the connectivity of surfaces. We say that the alternative treatment of Lifshitz transition in normal metal is to study Euler characteristic of the Fermi surface. In the same way, you can treat both superconductor and normal metal. So this is a message of this picture. Now, the question about smearing of the transition. Sorry. So what we did I had hopes that maybe Abrikosov and Garkov, who restricted by mean field, were too optimistic. No, it is difficult to struggle with classics. Actually, so we decided to introduce in free energy calculated for superconductor close to transition between gapless, we introduced the kinetic energy. Kinetic energy, I mean that we took into account the special change in the distribution of paramagnetic impurities. So we, in the style of Ginzburg-Landau, we added the gradient term, and we rewrote that gradient of delta is derivative of delta over parameter driven transition, and the derivative of this parameter over impurities concentration and gradient of concentration. So this is analog of kinetic energy. And we studied the stability, so importance of such fluctuations, and found that unfortunately for us, the transition is very stable. Actually, to destroy this mean field description, it is necessary that logarithm of the concentration of impurities will change at the distance of coherence lengths. Very good. So how to observe this transition? How to be sure that this is transition indeed is not only mathematical tricks, but experimental. Experimentally, we calculated the thermoelectric coefficient close to such transition. I will explain that it is possible to observe, and there is a method how to calculate thermoelectricity in superconductor. So we found that very similar. Why thermoelectric coefficient? Because we know the thermoelectric coefficient was the most sensitive to Lifshitz transition. So we decided to study this singular parameter also in superconducting state. We did corresponding calculations and found that indeed close to transition, you have asymmetric peak, which increases with increase of tau s. And I want to recall that the peaks close to Lifshitz transition are also asymmetric. And finally, it was proposed 50 years ago by Galpenin, Gurevich, and Kozub how to measure the thermoelectricity in superconductor. So it is necessary to create the ring with two different superconductors with different critical temperatures, and then to study the flux, magnetic flux through this hole, and this side by side with little Parkes quantization of the flux, you will have some non-integer contribution in terms of flux, which is proportional to the difference of thermoelectric coefficients in normal state. So, conclusions. The quantum phase transition between the gap and the gapless states of superconducting alloy with paramagnetic impurities is of the 2.5 order and hence has a topological nature. We found that the topological invariant in the form of the Euler characteristic changes from He equals 0 gap state to He equal 1 gapless state during corresponding topological transformation. It has been shown that the mean field approximation used by Abrikosov and Gorькov is very stable. Fluctuations of the impurity concentration remain irrelevant in the logarithmic scale. Such a topological phase transition can be detected by the parameter Fermi energy divided order parameter thermoelectric effect possessing the characteristic features which would clearly distinguish it from others. Thank you for your attention.
Дуже дякую, Андрію Андрійович, за чудову доповідь. Дякую вам за ваше вступне слово, за ваші патріотичні почуття, за підтримку України, Інституту теоретичної фізики імені Богомольця. Подякуємо, Андрію Андрійовичу.
Дякую вас за запрошення. Мені дуже приємно бачити всіх колег і друзів. Я сподіваюся, що цього року я буду мати можливість приїхати і випити дуже гарну чарку з вами нашої горілки.
Чудово, Андрій Андрійович, але це ще не все.
За нашу перемогу. За нашу перемогу.
Наразі можуть бути запитання. Шановні колеги, будь ласка, запитання до Андрія Андрійовича.
У меня есть вопрос, можно задать?
Да, будь ласка, Валерий Павлович Гусынин хочет.
Значит, характерная особенность вот Лившиц-перехода, проявление плотности состояния, это несимметричное поведение, да, вблизи сингулярности.
Да.
Такое несимметричное поведение возникает также, если в спектре квазичастиц возникают сингулярности Ван Хова более высокого порядка. Являются ли эти вещи связаны? То есть можно ли посмотреть сверхпроводимости для квазичастиц, дисперсионный закон, и, может быть, там тоже проявляются сингулярности Ван Хововские более высокого порядка?
Я с вами совершенно согласен. Но мы вот посмотрели только то, что я рассказал. Конечно, было бы интересно посмотреть и с другими спектрами, но вот мы пока ограничились вот этим. И так долго возились, чтобы понять, в чем, чтобы придумать эту Эйлерову характеристику. Это заслуга Юры. Вот я подходил через, как называется, из теории катастроф. В общем, мы не знали этой математики никто, поэтому нам пришлось учить по дороге.
Дякую, Андрій Андрійович. Ще питання, будь ласка. Маємо можливість задати питання, Андрій Андрійович, якщо є.
А вот это 2,5 порядок величины, это только единственный вариант или, возможно, какие-то другие варианты, кроме 2,5?
Хороший вопрос. У Моисея Исаковича Каганова были работы, серия работ, когда у вас меняется геометрия, а не топология. Тогда, то есть, когда образуются воронки на поверхности Ферми, такие вещи, это отражается, но не так сильно. Я думаю, конечно, могут быть переходы и других более высоких родов. Я пытался когда-то изучать, характеризовать, очень интересно рассмотреть, как меняются топологические переходы в зависимости от размерности пространства. Например, в одномерном пространстве. Что такое топологический переход? У вас есть отрезок, заполненный электронами, это Ферми-поверхность. А рядом появляется второй отрезок. Это малая область. То есть у вас есть только переход типа зарождения полости. Уже в двумерном случае вы можете, конечно, положить гривну и положить там рядом 10 копеек. Это будет переход двумерный типа зарождения полости. Но здесь имеется еще и возможность сделать гиперболу. И гипербола, это очень интересно, здесь от того, что вы перейдете, представьте себе, что вы меняете в гиперболе и меняете знак от двухполосной к однополосной в двумерном смысле. Ничего не изменится. Это все равно, что повернуть Ферми поверхность на 90 градусов.
Ну, да.
То есть получается, что переход типа разрыва перемычки возможен только в трехмерном случае. Понимаете? Вот. Чтобы он был... Нет, он есть в двумерном случае, но вот такой, чтобы получился однополосный, двухполосный, ну то есть это нужно говорить о сигнатуре матрицы масс. Вот. Ну и дальше обобщить это на четырехмерное и так далее. У вас появляются, например, сигнатуры плюс-плюс, минус-минус в четырехмерном пространстве. Ну вот, поэтому я как-то двигался вот в этом направлении по классификации разнообразия топологических переходов в пространствах различной размерности.
Ясно. Дуже дякую.
Так, шановні колеги, є можливість задати ще одне питання.
Ну, у мене є питання. Мені здається, що не враховується ще одна характеристика, а саме характер пар. Коли енергія Фермі дуже низька, то рівень Фермі чи може ще давати додаткову характеристику, тому що можуть ой Боже, як це буде образовуватися?
Утворюватися.
Утворюватись локальні пари. І тоді буде додаткова характеристика від енергії Фермі в цих переходах. Коли одна енергія Фермі висока в великій зоні, а в малій зоні чи низька.
Енергія Фермі є єдина.
Вона єдина, але може залежати від того, як далеко вона відійшла від нуля, від своєї зони. Там, де вона відносно низька, тоді вона має бути, утворювати локальні пари. Локальні пари і пухарівські пари – це дещо різні утворення.
Я думаю, що тут механізм другий. Я думаю, що, як я розумію, без as I understand, sorry, because I don't, I never learned physics in Ukrainian, unfortunately, because I finished the school number 145. And, okay, so actually what happens? What is the effect of paramagnetic impurities on superconductivity? Imagine the Cooper pair with one electron up and another down. Then they approach magnetic moment. Magnetic moment affects on these two electrons in different ways. And Cooper pair is braked. It is braked and these electrons become free. Then, after some time, they recover Cooper pair. So the question of exists superconductivity or does not depends how often these electrons will meet magnetic moments. If they have time to recover, so imagine that person break the leg. It is emergency, bring him to hospital, and in half a year, he will recover. But if he will break legs every 3 months, he will not be able to walk. The same with superconductivity. I mean, so here I think that I don't, but here, where do you see the second? Here there is no small void of Fermi surface in the model which I discuss. I discover the large Fermi surface and superconductivity due to electron-phonon interaction, plus the effect of paramagnetic impurities. So I don't see here, there is no Lifshitz transition in sense of normal metal. Here, there is a normal Fermi surface. So I don't accept this.
Дякую, Андрію Андрійовичу. Шановні колеги, давайте ще раз подякуємо доповідачу за чудову лекцію і такі вичерпні відповіді на питання. Добра і здоров'я вам, Андрію Андрійовичу. І я прошу до слова
Дякую,
Бориса Євгеновича